All right, going to talk about normal distribution, normality, probabilities, confidence intervals. Going to spend hopefully a reasonable amount of time really talking about confidence intervals. Hopefully you've gone through, taken a look at some of those papers that we've assigned, but thinking about how we incorporate these, what we take from that interval estimate, and how we incorporate it into our interpretations of things. So just as a recap, okay, so last week, talking about means and standard deviations. If we have means and standard deviations, it starts to tell us some useful things about sort of where a person's score falls relative to the average of the distribution, right? But in and of itself, a single raw score, very limited information, right? If you just give me a score, I don't have a good idea of where this falls relative in terms of rank, relative to other scores in the distribution, how big it is, and most importantly, perhaps, the probability of observing this score relative to everything else in the distribution, okay? This starts to get at the very sort of fundamental foundations of our inferential statistical procedures. So what we're going to talk today is starting about turning things into standard scores. Standard scores allow us, give us a metric to put individual raw scores on. We can start communicating information about that individual score, the mean, standard deviations, all placed in a single value, okay? So it's a very condensed metric that gives us a lot of different information. We're going to use our standardized scores, look at position rank relative to other members of a distribution, right? And so if you say here is an individual with a z-score on some measure of 2, right? What can I already tell about that person's score relative to the larger distribution? Okay.
Saying that z-scores 2?
Yeah.
That there are 2 standard deviations away from.
Perfect, perfect. 2 standard, so this person is 2 standard deviations above the mean of sort of the distribution, right? So what am I already inferring about this person's value?
I mean, with normal distribution, in the top 1%.
95, yeah, no, 2.5%, something like that, yeah. So already, and depending, and so this is where it starts, depending on sort of what our assumption is of the distribution, can actually start to give us sort of ideas about probabilities and things along those lines. And this is where all of our inferential statistical tests are. We have a distribution of scores, and then we're assuming it's a known distribution. So if we know where that score falls on that distribution, we can start telling you the probability of randomly selecting a score at that level or higher, things along those lines. Okay. So standardized score, or example, IQ, this is just a nice, good example. This is a measure or an assessment that's very, very well normed. Mean value is 100. Now this is an arbitrary mean value, right? We decided 100's a good score to have, right? Like IQ scores aren't out of 100 questions that you did, or 200 or something or whatever, right? And then we have a known population standard deviation here of 15. So, but one of your numbers suggested that you all were, maybe about 2 standard deviations above the mean in intelligence. That would be fantastic. It might be a little bit generous. 2 standard deviations above the mean would put us all at IQs of 130, which are quite high. It's possible. It's possible. I don't know that I'm quite that high up there yet. I'd like to think that would be the case, but in general, right? So we've got a standardized distribution with a known mean, known standard deviation, right? And so we can start to infer things about the characteristics of individual scores in this distribution relative to others. Z-score is going to be a specific standardized distribution having a mean of 0 and a standard deviation of 1. Okay. Mean standard deviation defining features of a z-score distribution. By definition, if you have a z distribution, the mean has to be 0, standard deviation has to be 1. Okay. A couple components we're looking at. Value. This tells us the number of standard deviation units from the mean of any given score. Trent identified that 2 standard deviation scores, that z-score of 2 is 2 standard deviations above the mean. This is absolutely correctly. Anytime you see a z-score, you should be thinking standard deviations. In fact, anytime you see a sort of group level effect size, you should be thinking standard deviations. When we get into t-tests and things along those lines, standard deviations are the unit we're using, right? And so it's not just some random arbitrary number of d equals 0.8, right? That d equal 0.8 means that whatever comparison is two standard deviation, or about 0.8 of a standard deviation above some reference point, right? So our value for our z-scores, again, in terms of standard deviation, and then our sign tells us if it's above or below the mean, right? So now this is going to be important as you're going through and working through problems for set 3. Sometimes it's easy to get things flipped around and get your sign wrong, but if you got your sign wrong, that's kind of a big deal, right? If you meant to see someone's 1.5 standard deviations below the mean, but you forgot that negative sign, you're communicating that your score is actually 1.5 standard deviations above the mean. It's kind of a big deal, right? So you want to make sure that you're paying attention to that sign. Standard z-score, or z-distribution, here's 0, which is our mean. Standard deviation z equals 1, we got 1 standard deviation above the mean. Negative 0.5, half standard deviation below, 2.5, 2.5 standard deviations above, 1 standard deviation below. It's nice, it's easy, efficient, it communicates a lot of information, and this is sort of our base distribution in terms of thinking about standardized scores. Again, all this stuff, probably a lot of review stuff that you remember from undergrad statistics, but any questions with any of this up to this point? Okay, cool. Formula for transforming raw scores into z-scores, pretty straightforward. Take your raw score minus the mean of your distribution and divide by the standard deviation of the distribution. Okay. And so what we can do then, using this formula, is start to very easily start calculating z-scores for things, particularly if they're in nice numbers, right? So if we have a corresponding z-score, so our distribution has a mean of 12, mean of 10, standard deviation of 2, what's a corresponding z-score for a raw score of 12? 1, right? How did you get that?
I took the raw score, subtracted the distribution mean, and divided by standard deviation.
Right, yeah. So we can plug it through that formula, quick and easy, we get it there. Or from a conceptual level, right, you say my mean is 10, I've got a standard deviation of 2. So a score of 12 is exactly 2 units above 10, right? So basically this is just literally 1 standard deviation above the mean of my distribution, right? And so you can work back and forth with this. Some of this stuff you'll be able to do in your head. Sometimes you need to use a formula there. Stephanie, what about for a raw score of 8? What's our z-score? -1, right? We are literally, if our mean is 10, 8, that's literally 1 standard deviation below the mean, right? What about 11, Gabby?
0.5.
What's that?
Or a half. 0.5
Yep.
above.
Right? Half a unit, half a standard deviation above, right? What if, Rachel, what if we got a different distribution with a mean of 34.6, standard deviation of 8.2, what's your z-score for a score of 17? Do you have a calculator?
I don't. I was gonna say if I had a calculator.
Zach's got it. Zach's got your back today.
Okay, thank you, Zach.
Remember to bring your calculators. You can use your phone in here, I don't care, but tests you have to use your actual calculator.
I got kind of an ugly number, but
Yeah.
negative 2.146. Yeah.
What did you get? 2.146?
Yeah, negative.
Negative 2.146. Right. Okay, so we've got about negative 2.15, right? So we've got a little over 2 standard deviations below the mean, right? Easy, straight up algebra. Today's going to be a lot about algebra, right? But just going through and using this formula. These ones you can kind of do in your head. These ones are going to be a little more tricky. You probably want to run it out, okay? Just a heads up, as you're going through for this, these next couple of problem sets, I'm going to have you doing problems like this. Just please, on your handwork that you're turning in, make sure that you've written out exactly what you've got, the process you've done, and try and make it semi-organized and sort of in all square with the world. So Tess and I can go through and take a look at that when it comes up. Okay. So, all of our standardization, typically like our test statistics, things like that, are always, we're gonna be working with some sort of standardization formula, and it almost always follows this same ratio format, okay? Get used to ratios, fall in love with ratios, be looking for ratios whenever you can, because it just starts to tell you a lot about what's going on with these statistics, right? I want these to be more than just a number for you, to actually sort of looking and sort of understanding what's going into the calculation of these, and then the types of things that start to influence that, right? As our standard deviation increases, what happens to our z-scores? All of the things held constant. Candace?
As your standard deviation increases,
Mhm.
the z-score gets smaller.
Right, right. So we got much more variability. So we can have very large differences, like, oh, that seems like a big difference from the mean. But if our variability is really huge, it's probably not, right? And so just thinking about what's going into these formula, and sort of if I start playing around with stuff, what impact that has on my test statistics starts to become important when you're doing your own research, and you say, oh, I'm looking at my stuff and I'm like, sweet, I've got a great huge difference. Certainly this will be something that I can publish. Until then, you actually run your statistics and you're bummed, because that huge difference is a huge absolute difference, but in the context of a larger distribution of scores, it's actually not all that shocking. Right? So, graphing raw scores and z-scores, again, something I'll encourage you to do as you're working through this set. Actually graph out these, your normal curves, and so they're helping you organize things. So here's our normal distribution, here's our z-scores, 0, 1, 2, 3, we've got standard deviations out, and we can, down below, start to map actual scores onto those z-scores, right? So 0 is my mean is 34.6. Go standard deviation above, I add 8.2 to that, there's that, 8.2 to that, same thing there, and then I can go out and plot my score. I got negative 2.15 about, so that's down here. Just making sure, just think about this as your check, right? Your plausibility check. So this is the score that I've calculated. Does this make sense? Actually take a look at your distribution, draw a little diagram. Does it make sense that this is probably about where this score would fall? It's going to help you out and help you from falling into silly mistakes. Okay. People see what we did here with this? Make some sense? Okay. What we can also do with that Z formula, start to restructure it, right? With a little bit of algebra, we can take that z-score formula and start to go through and solve for any value if we have enough information from the other stuff. Right? So let's say we've got a raw z of 1.96. And so what are we looking for? So what's the raw score if we found a value that has a z-score 1.96, a mean of 73.6, and a standard deviation of 14.8. So we're looking for, so we've got z equals x minus mu over our standard deviation, right? Well, what we want to know is what that raw score is, right? So we can algebra things, right? Oops, not that, that stays where it is. And so we've got x minus mu. We can say, well, we want the raw score, so let's add mu, that cancels out, and then we get x equals, okay. With that, and then we can just plug stuff in, right? So if we have our z-score is 1.96, and our standard deviation is 14.8, and my population mean is 73.6. My value 102.61. Okay. Again, pretty straightforward stuff, but if it's been a while since you've played around with algebra, it can get a little bit tricky. Okay, so people see how we went through and got those values. So let's say population population with a mean of 65, a score of 59 corresponds to a Z of 2. Right? What's the standard deviation? If we go through and run our algebra, we get standard deviation is x minus mu over z. Okay. If we start plugging that stuff in, we get standard deviation of 3. Now, this is the thing. If this makes sense, just let me keep going. If it doesn't make sense, stop me, because what I don't want to do, if you're like, yeah, we covered this in 6th grade, we don't need to cover it in grad class, let me know. I don't want to bore you with that. But if you're rusty and it's been a while, stop, and I can show you how we ended up with that. Okay? People comfortable with sort of getting from point A to point B? Okay. Because if you are questioning it, probably someone else questions it, so don't feel bad about asking you to stop. So we got a population here with a standard deviation of 4, a score of 33 corresponds to a Z of 1.5. What's the population mean? Again, we sort of run our algebra. Population mean equals x minus z mu, and we end up getting population value of 27. Okay. So this is all just going through manipulating these equations back and forth to get the type of stuff that you want. Again, at the end of the day, how often will you do this? Probably not a lot, but if you have an occasion to do it in order to figure something out, this is going to be nice. You know where I use this stuff? Is when I'm reading a paper and someone hasn't given me the mean of whatever they've done, or I need to find a standard error of something, but I don't have enough information, but I've got pieces and parts. It's nice to be able to take what I know the formula for a test statistic is and reverse engineer that to be able to find a standard deviation, maybe because I'm trying to find an effect size for what they found, or I'm trying to run a power analysis and I need to know what their means are. And these jerks didn't tell us what the means and standard deviations were, so now I've got to go through and reverse engineer statistics to figure out what it is, right? I can do that. I would prefer not to, but I can if I need to, using just some of this basic stuff. Okay. So, utility of z stores, exact location of an x within the distribution. Other thing that's nice about this is we can take scores, form a standardized distribution, and what we can do is we can start to compare scores across distributions, no matter what the mean standard deviations of those individual distributions might be. Okay? So, for example, Henry, with an I, is participating in a personality study, right? Scores an 87 on a measure of conscientiousness and a 73 on a measure of extroversion. Okay. Which personality trait in Henry is more prominent? What do you think, Stan? What's that? Conscientiousness? Maybe, right? But if these are different measures with different distributions, I don't know, right? This is a higher score than that, but without some context about mean standard deviations, things along those lines, I don't know. Maybe conscientiousness, mean of that distribution is 100, and the mean of extroversion is 50. We've got two very, very different scores right here, right? What I can do if I know the hypothetical distribution, sort of the normative distribution of these scores, what I can do is I can translate both of those into a z-score and then be able to say, for this individual, do they tend to be higher than the rest of the world in terms of extroversion or in terms of conscientiousness, right? With this information, I don't know. Same thing, I'm Claire. Claire is, that's me. This is a problem I ran into at one point, so not Claire, Josh, is trying to create a composite quality of life variable based on scores from 3 different measures. Okay, so you got 3 different quality of life measures, and I want to combine some sort of composite score. Yeah, why don't I just?
Well, they might all have different scales, so.
Yeah, yeah. So yeah, one of my composite of life goes 0 to 10. Another one's an average of a 0 to 5 scale. Another one goes from negative 14 to positive 14. Right? If I just go through and add those things up, I'm going to have a mess. Right? There's zero interpretive value to. I mean, I can do it. You just can't interpret it as anything. Right? But if what I do is I go through and calculate, give everybody a z-score for each one of those, and then maybe take the average of my z-score or something like that, then all of a sudden I'm starting to get something that is not a perfect interpretation, but at least it's something that I can tell. In general, these are higher scores are going to tend to correspond to people who tend to fall higher in their distributions of quality of life, things along those lines. Problems with it, but I guess in the absence of a better solution, it's workable. To this point, we typically talking about z-scores falling on a standard symmetric bell-shaped distribution, right? And when we think about z-distributions, we always think of our z-table, right? And it's this nice, lovely, smooth distribution that's symmetric. Important to realize, and people get tripped up on this, that just because you've created a z-distribution doesn't mean that you have a normal distribution, okay? So just because you created z-scores, it doesn't mean that you have some sense of normality or that the shape of your distribution is going to change at all. Distribution of your z-scores is going to be identical to the distribution of your observed scores, okay? They're the exact same thing. You didn't change the shape of that thing at all. All you just did is change the metric. So now the mean is always going to be 0. Standard deviation is always going to be 1, right? Which you've got a standard you've got a standardized distribution that have a set mean and standard deviation, but do not assume that just because we've transformed things to z-scores that we've improved the distribution or that the distribution is normal or any other such thing. Okay? If we want to go through, we want to create a standardized distribution here. So we've got raw scores 0, 6, 5, 2, 3, 2. And if we calculate mean standard deviation, we've got a mean of 3, standard deviation of 2. Right? So if we go through, lay this out in the table, score of 0, 1.5 standard deviations below the mean, z-score of negative 1.5. Score 6, 1.5 standard deviations of the mean, 1.5. Score of 5, standard deviation above the mean, 1 standard deviation, z-score of 1, below, so on and so forth. Right? So what we've done is we've taken our raw scores, translated these into z-scores, and this is pretty easy to do in our head, right? We could run this through our formula if we needed, but all this makes sense, right? Issue is if we go through and plot these two things out, so these are our raw scores, right? I mean, we only got 5 values, right? So it's not much of a distribution. But when we go through and we create a histogram of the z-scores, they're identical, right? The only thing we did is change this number down here. Now, if we're assuming that the theoretical distribution of whatever it is that we're measuring is normal, then we can start to make some inferences on the likelihood of some of this stuff happening. But just remember that taking a set of scores and changing them over to z-scores doesn't do anything to the distribution. Okay? All you're doing is you're saying we're just making the mean of this distribution 0, standard deviation of this distribution is 1. Questions about this? All right. So z-score is one type of standardized distribution, but there's all sorts of different types of standardized distributions we see in some commonly used formats. T-scores, these are scores that will have a mean of 50, standard deviation of 10. Okay. T-scores, you'll see this in some like intelligence testing and things like that where you've got a T-score. IQ scores, standard mean of 100, standard deviation of 15. SAT scores, mean of 500, standard deviation of 100. These are all standardized distributions, right? It's just our z-scores are a special sort of version of this where their mean is 0, standard deviation is 1. But if we want to take raw scores, translate them into T's, IQs, SAT scores, things along those lines, quick and easy way to do this, take our raw scores, change them into z-scores, right? And then take our z-scores, make those into our new standardized scores with the specific mean and standard deviation, okay? The z-scores, what you want to do first. So let's say that we have a set of exam scores and we want them to have a standardized mean of 500 and a standard deviation of 100, okay? Distribution of raw exam scores, actually, so the raw scores, mean of 57, standard deviation of 14. Okay? What we want to do is calculate standardized scores based on those values right there. So again, what we would do, we've got our 4 scores, right? 64, it's a half standard deviation above the mean, right? So we've got a z-score of 5. So what we need is we're saying that this score is a half a standard deviation above sort of what I want my mean to be. And so I take that z-score, multiply it by my standard deviation, and add it to my standardized mean, and I get a standardized x of 550. Same thing, 43, this is one standard deviation below the mean. So if I just calculate my z-score, I get a standard z-score of -1. That means that this score falls one standard deviation below whatever mean it is I'm trying to set. So if my mean is my hypothetical mean of the distribution is 500, and I subtract 100 from that, I get my new standardized score of 400. Same thing, 57, that's right at the mean, z-score of 0, equal to my new standardized distribution. 71, standard deviation above the mean, take my z-score, multiply it by my hypothetical standard deviation, add it, 600 here. And if we take this, what we can do is then, as a plausibility check, go through, map this out. We've got our standardized, our bell curve here. See, these are our raw scores, mean of 57, standard deviation of 14. And all I'm doing is I'm just playing around with the scale. I could make this standardized scale whatever I want. I could make the mean 1005.6 with a standard deviation of 1,000,000 if I wanted to, right? I don't know if that would be a useful distribution, but it's a free country, I can do whatever I want, right? So we've got a z-score, our z-scores here, our raw scores here, corresponding to our standardized scores, and then just making all that, sure all that lines up if you want to go through and make sure that you've done this correctly. Okay? Seems pretty easy, straightforward when you actually get into it. It's easy to get things flipped around and confused, but just sit down, make sure you're giving yourself enough time. And again, this is a nice strategy for making sure everything's lining up the way it's supposed to. Questions about changing this metric from one thing to another? Cool. Okay, so why is all this important, aside from parlor games and things to do when you're drinking beers with your friends? Okay, let's create some T-scores. Quiz each other on what it is, draw some graphs, even cool stuff like that. What we do is that one, standardization is looking at it and giving us a process by sort of identifying individual scores from the mean, individual scores in the distribution, comparing to other scores. But when we have a set of scores that follow some known distribution, okay, or assumed distribution, what we can start to do is start assigning probability values of obtaining scores in certain regions or scores above a certain number based on that known distribution, okay? So what we can start to ask are questions like, what's the probability of randomly selecting a score equal to or greater than some value? Here's our normal distribution, right? And we know a normal distribution. The nice thing about a normal distribution is this is something that sort of many different types of phenomena fall kind of on this natural bell curve, right? But what we know is that between certain standard deviations, certain benchmarks, we have a certain level of probability of falling between or beyond certain portions of this curve. So frequency distributions, some of those bar graphs that we've been looking at, direct relation to probability, okay? Frequency distribution, the graph corresponds to different population, or different portions of the population, and because proportions and probabilities are equivalent, what we can start doing is representing areas under the curve as percentages or the likelihood of randomly selecting certain values if we sort of just doing this and pulling things in, okay? So for an example, just to kind of cement this in your brain, say we have a population, and this population has values of 1, 1, 2, 3, 3, 4, 4, 4, 5, and 6. This is our population. These are all the scores in the universe that exist of this thing, right? This is the population. If we go through and we plot out a frequency graph, this is what that looks like, right? So a very simple example, but if we go through and we say, what's the probability of randomly selecting a score greater than 4, right? If we want to do this in probability notation, or P of X greater than 4. Okay. What's the answer to this question, Bijan? What's the probability of randomly selecting a score greater than 4 given this distribution? 20%, absolutely. How did you calculate that? Yeah, exactly, right? So we've got 10 scores, right? There's 2 scores that are greater than 4, and so all we need to do is say, well, there's 2 of these relative to the 10, is 20%, right? So our probability is 20%. Pretty easy to see with this frequency distribution. What we can then do is take this sort of basic concept and start applying it to known distributions, right? So a normal curve sort of is a distribution commonly observed in nature. Like lots of different things tend to fall in some version of a normal curve, right? Things like height, things like different personality traits, right? Things that we see in general. So we've got our mean. We've got some people scoring higher, some people scoring lower. As we get farther out toward details, the likelihood of, or the frequency at which that event occurs becomes smaller and smaller. A nice bell-shaped curve. Our normal curve has a symmetrical distribution. Highest frequencies occur in the middle, taper off as we get out to the extremes. Mean, median, and mode, all exactly the same value on that hypothetical normal curve. Okay? And because of calculus and other fun things, areas underneath different portions of that normal curve have known probabilities. Okay? And our z-scores start to serve as benchmarks for sectioning off certain probabilities falling underneath the normal curve. Anybody here sort of go on with math and sort of get into Calc 2 and above? If you did, all this starts to become shockingly familiar. I was taking Calc 2 at the same time I was taking my undergraduate statistics course and trying to figure out how to identify areas under the curve. And so I was like, oh, this isn't just a trick. This is actually sort of what's going on with this, right? So here, when we've got our sample frequency, 2 blocks out of 10 blocks, 20, the likelihood of randomly selecting either this value or that value, 20%, right? And that's easy. We can take a look and say, yeah, that makes some sense. We can do the same thing using those same basic principles and some calculus. Start to answer the same questions, assuming that a set of scores follows a hypothetical normal curve, right? So here, in this example, our mean is 34.2. We've got a standard deviation of 6.8, right? Assuming that whatever I'm measuring here follows a normal distribution, what I can start to do is start to answer this question, what's the probability of randomly selecting a score greater than 45? And we're not going to do this right now, but it's the same thing, right? So 45 is going to be somewhere beyond 1 standard deviation, right? So what I can do is calculate that z-score, figure out sort of where that is, and then start to determine what the probability of randomly selecting a score at or greater than 45, based on sort of stuff that other people have worked out that we don't need to work out on an individual basis. People sort of understanding sort of what the sort of basic principle going on with this stuff? Okay. So, normal distribution. So lovely normal formula for our normal curve right there. I'd like to have that big like landscape above my computer, something like that. I haven't found it yet. If you do find something like that, let me know. I will purchase it. Normal distribution, right? We know under this smooth hypothetical distribution of scores, values between -1 and 1, about a little over 68% of the population falling between that benchmark of -1 standard deviation and 1 standard deviation. We stretch this out to 2 standard deviations, we're capturing about 95%, right? So we've got about 2.5% in the upper tail, about 2.5% in the lower tail, and then as we go out and out, it gets smaller and smaller, more extreme, right? We get smaller, the probability of selecting a score at or greater than z-scores greater than 2 starts to get very, very small, right? So what we can do is we can start to use this to start assigning specific probabilities. So we've got a question here. Population of adults' heights normally distributed with a mean of 68 inches and a standard deviation of 6 inches. Okay? Given the properties of normal distribution, what's the probability of randomly selecting an individual at or taller than 80 inches? So what's the likelihood that we just, if we sort of put our blinders on and randomly pick something up out of the population of humans and have that person be 6'8" or taller? Okay. So what we're going to do here first, we're going to sketch out the distribution, right? And I'm going to strongly encourage you to do this as you're working through these problems, at least till you get the hang of it. Say, here's our normal distribution, right? Mean 68, standard deviation is 6, so 1 standard deviation is going to be 74, so to move out there. And this is just to give you a visual to make sure your numbers are making sense, right? What you want to do, identify the exact location of 80 by calculating the z-score for that, right? If 68 is our mean, standard deviation is 6, 80 is 2 standard deviations above the mean, right? So we get a z-score of 2. So we have this z-score of 2. And then what we can do is we can determine probability of the area of interest by using a unit normal table, okay? And this is the thing that starts to become tricky as you're going through and doing these processes. And again, would strongly encourage you to physically do this on a sheet of paper. Say, okay, what I'm looking at is the probability of selecting a score of 80 or higher, right? So this shaded area is what I'm looking for, right? This gives you a visual representation of what I'm looking for is probably a very low number, right? It's probably a low probability, right? This is going to help you as you work through your unit normal table. I gave you a copy of the unit normal table. And pull that out, take a look at it. Some things to just as a refresher for your unit normal table. Here, you have your z-scores, right? These are your actual z-scores you've grabbed. And what your normal tables will have is the area or the probability in the larger portion of that distribution and in the smaller portion, right? So if I say I have a z-score of 0.4, right? So this individual, or my reference score, is exactly 4/10 of a standard deviation above the mean, right? So my z-score is here. What's the probability of selecting someone below that score? Well, it's not quite a half standard deviation. So the likelihood, about 65.5% of the entire distribution is below this, right? Smaller portion, that's the shaded portion here. About 34.5% of the population is above that score, right? Now, Howell, because he's a good guy and sort of a thinker in his head, also giving you this proportion of the probability found between the mean and sort of whatever your cut point is. This is really helpful for some of the things that you'll be doing because what you can say is about 15.5% of the population falls somewhere between the mean and a standard, 4/10 of a standard deviation above, right? Or translating that back, we can say the probability of randomly selecting someone who falls between the mean and the 4/10 of a standard deviation above is approximately 15.5%. Probably a refresher, but it may have been a while since you've gone through this with your undergrad statistics. Is this making sense to people? Okay, cool. So, using our unit normal table, assuming normal distribution, probability of randomly selecting a z-score at or greater than z-score my distribution, here's 0, whoops, 1, 2, -1, -2, okay? And what I want to know is I want to know the probability of randomly selecting a z-score or a score that corresponds to a z, oops, greater than 1, okay? Gabby, can you give me an answer for that? Using your unit normal table. Okay, now this is, thank you. Thank you for getting that wrong. Because 84%, right? Now, if you go through and take a look,
16%.
right? Is this
Oh.
sort of 84%? Nope, this is sort of small detail. So you look at that, you're back, nah, I got that backwards, right? So probably you're looking at the sort of everything lower. What's your probability of randomly selecting a score greater than a z of 1?
16%.
Yeah, 16, right? And if you go through and it's a 15.87 or 0.1587, so 15.87, right? So just going through and as you're calculating things, try and be specific just so I'm not trying to gauge if you got something wrong or if it's rounding error or something along those lines, right? Okay. What about Rachel? You got, assuming the normal distribution, probability of selecting a z-score at or less than 1.5.
93.32%.
93.32%, right? So if we're saying 1.5, it's all of this stuff underneath, so the big chunk of the curve, right? So 92% seems like it makes some sense. Okay. Stephanie, what about portion of the normal distribution that's contained beyond -0.5? And this one's a little bit tricky, right? Beyond negative, which beyond, right? Because here's my point, right? And beyond could be above, beyond could be below. If we take a look at the notation here, what are we looking for? Scores that are above -0.5 or less than -0.5? Oh, nope. Less than, right? So if here's our 0.5, negative, right?
Yeah, I meant the left way, sorry.
Left way. Oh,
Yeah.
okay, gotcha. Okay, be careful. So if 0 is 50, 50 is here, 50 is there. This is what you're looking for. Then it has to be a number less than 0.5.
Oh, no, I looked at the wrong thing, just
Okay.
kidding. Like 61, so. I forget if you read it when you asked the question, do you read it in 61 or do you do it
Okay,
61%?
again, not, because this green shaded area is what you're looking for, right? And if this is 50%, this is obviously visually smaller than 50%, so you've got to have a number that's less than 50. Right? And this one's a little bit tricky.
Would it be identified as a smaller portion?
It's gonna be, yeah, it's gonna be.
No, I mean labeled
Or
here.
excuse me, okay. So what is the tricky part about this question here in terms of your unit normal table? What's that, Candace?
There's no negative scores.
It's a negative z-score, right? But our distribution is symmetrical, right? So anything that's negative, we can go ahead and say is positive, right? And so if, what I'm gonna do is I'm gonna find a z-score of 0.5 here, right? So I got it, right? And then if I'm going to look at what's in the tail essentially, right? So if you flip this around in terms of mirror, say, here's 0.5, right? And what I'm looking for is things above that. It's gonna be equal in proportion to what's below and what's above, okay? So if you go down through and you take a look if this is what you're looking for, and we look at our z-score, so we have the larger portion is 0.6915, the smaller portion is 0.3085. Which one of those are we looking for in this problem?
So when it's a negative, you switch the title. What is smaller and what is larger in this graph? So
Well,
that you can,
Not, this is still the smaller portion, right? Because you're looking at the smaller portion of the distribution here, right? So even though it's negative, and this is why it's helpful to go through, plot these out so you can identify exactly what it is that you're looking for, right? So in this case, what we would do is say, okay, I want what's going on in the smaller portion. Now I know it's a negative, but on my z-chart, I'm just gonna go down through, find the z-score, and visually what I'm looking for is what's in the tail here, right? And so I'm gonna take this, shave this off in the tail, and then say, well, I've got two options. It's either, my answer is either 69% or 31%. Okay, this is in the tail, it's in the smaller portion, so it's gonna be 0.3085. Okay, so this can be surprisingly tricky as you're going through and figuring this stuff out. But yeah,
Because it's less than and not less than or equal to,
yeah.
would you go to the, z-score of 0.49 instead, or no?
That's an excellent question, right? So here, some of these were saying less than or equal to or less than. Technically, from a theoretical perspective, it's impossible to have a z-score of exactly 0.5. Or it just gets, the probability gets asymptotically small as our precision gets higher and higher. So functionally, there's no difference. You're still using the same z-score here, whether or not we're saying at or below a certain level. So that's a good point. But from a theoretical standpoint, because this is a true ratio, a true interval scale, we can get increasingly in small z-scores, right? So if we're working with like chemistry or something like that, where we're looking at like exponential functions of something like that. So don't need to worry about that. We can just go through and ignore that and sort of just, main thing we want to do is figure out which proportion of this graph are we trying to look at and making sure that the proportion that we're coming up with is sort of systematic on that. Questions about that? All right. Okay. Some more stuff that we can do. What z-score represents the top 10% from the remainder of the distribution? Trent, what are we looking at there? So what's different about this question?
Z-score of 1.28
Exactly. How did you find that?
by finding where the small proportion was 10%.
Yeah, absolutely, right? So again, if we're mapping this out, right? So here, we want to know what z-score corresponds, separates the top 10% of the distribution off from the rest of the stuff, right? So what we do is we say, okay, we're looking at what's going on in the tail. We want 10% here. And then going down through your smaller proportion list and finding the value that's as close to 0.1 as possible, and then looking through and finding the z-score there. For normal distribution, what z-score forms the boundaries that separate the middle 60% of the distribution. Zach, you want to field this one?
So it would be positive and negative 0.52. Your z-scores.
0.52? So this
Oh,
is
no, I got it the wrong way. I was looking at some Oops. Hold on. Okay, on this I have
8.4, 8.5, I think
Yeah.
8.4 is actually closer, right? This one's tricky, right, because what we wanna do is we wanna find out middle 60%, right? And if this is 0, what we need to find it's symmetrical, right? So we wanna say, all right, going down through, and we can use this mean to 0 column and say what contains 0.30 here, 0.30 here. Now it's symmetrical, and so if we go through, we take a look at our z-score of 0.84, that gives us a proportion between the mean and that z-score of 2.2995. We go one up, it's 0.3023, so this one's probably closer, right? And so z plus or minus 0.84 are kind of the bounds of that middle distribution, right? That captures 60% of randomly selected values between there. No, that's the last one, so no more torturing you with these types of things. But you can see, like, this gets tricky, right? And with a lot of this stuff, you're like, oh yeah, no, that seems fine. When you actually sit down and do it, it can trip you up, so just go through and make sure. And again, there's no shame in sort of having your, whatever you turn in be littered with little distributions, right, and sections. It will help you because this gets increasingly tricky as we're moving forward stuff. So, human normative table calculations, we can go from X's to Z scores. We use our Z-score formula. We can go Z-scores, probabilities or proportions using our normal table. We can't get from X's to probabilities without going through Z, right? So as you're going through and working on these, like, here's the mean and standard deviation of the distribution, what proportion of values are gonna fall sort of between the mean and a score of 86, right? We need to go through Z-scores to get there and back and forth, yeah.
Slightly off topic, but for our upcoming work,
Mhm.
do we need to draw distribution tables? And okay.
You don't need to draw distribution tables for anything. If you feel like you're good, unless I've actually told you to draw a distribution table. But
Just showing our numerical work.
numerical work, yeah. And so again, this gives me an opportunity to go back through it, and if you've gotten things wrong, I can go figure out what that is. Or if your score is a little bit different than my score, I can go through and see what values you plugged in and see, is this rounding error, or is it sort of a mistake somewhere along the way. Again, they're really intense, and you're like, oh, well, why does it matter if I'm 0.3 of a point off? That's 300 through, something like that. What I want you guys to be able to do is use these homeworks sort of down the road and go back through. And so if you've got errors and you've actually procedurally done something wrong, I want to catch that, not to tax you, but just so that you don't continue on indefinitely and say, oh, this is the way I do something. Okay. So. Okay. Most cases, what we're going to be interested in doing with our test statistics and things like that is identifying the probability of finding the score above or below a specific value. Going to transform X's into Z's, look at corresponding populations. So what we can do here, so IQ scores from normal distribution, mean of 100, standard deviation of 15, probability of randomly selecting an individual with an IQ score less than 130, right? Same type of problem here, right? Before we're just looking at Z values, we're just taking this another step. So we're taking, here's our mean standard deviation, here's sort of the score we're wanting to find, and so what is our Z-score for this question? 2, right? 2, and so our question is what's the probability of randomly selecting an individual with an IQ score corresponding to 2 or lower, right? So Candace, what's give me a probability for this question here?
95%.
95. What's that?
95%.
Not exactly 95%. Go through, take a look at your, so we're looking at a Z of 0.2.
Oh.
Or excuse me, a Z of 2.
Oh, okay.
What's the actual probability?
Uh, 97.7%.
Yeah, okay. And see what happened here, I see where you made your mistake, is usually when we're thinking about normal curves, right? We've got, oh, this is sort of this, the value, the probability of having a score that falls between plus or minus 2 standard deviations, right?
Mhm.
Here, what we're interested in is what's the likelihood of finding someone who just has an IQ score below 130, right? And so we catch that tail that's
Right.
outside of our standards, right? So again, taking a look at that, we want everything down at the lower end of that distribution. Okay. Changing this up a little bit. Actually, what time is it? I'm just- Making incredible time here. A little bit different. Okay, here we've got a highway department conducting a study measuring driving speeds of local highways. They observe the speed with mean is 55 and a standard deviation of 10. Distribution of speeds was approximately normal. What proportion of cars are traveling between 55 and 65 miles an hour? So here, again, setting this up. Here's our curve, right? And we want to know cars traveling between 55 and 65 miles an hour. So what do we need to do first? Translate things into z-scores, right? So can someone tell me what our z-score is for 55 miles an hour? Is, what is it? Negative 0.4?
Yep.
Okay. And what about 65?
Positive 6.6.
Okay. And so now what do I need to do? He's going to find out what the likelihood of randomly selecting a driver that's somewhere between negative 0.40 and plus 0.6. So we're going to look at values from the mean, right, to 0.6. And so I'm getting that, of course, falling into a probability of 0.2257, and between the 0.4 and the mean, 0.1554, right? And then what do we do with those two values?
Just plus these two answers. So
Just add those up,
Yeah.
right? And so we get probability of 0.3811. And so again, using this unit normal table, we're saying, all right, and this is where some of this stuff starts to become important, right? So you're plotting out your curve, you're saying, all right, we want to know how many, what's the likelihood of randomly selecting a driver coming through this traffic stop who's driving between 55 and 65 miles an hour? Well, given that we have a good idea about what this distribution looks like, we think it's approximately normal. Z-score for people who are driving a little bit under, and z-score for people driving a little bit over. Calculate the probability here, and we've got it going on. What happens if we want to take a look at what proportion of cars driving between 65 and 70 have I picked on for a while? Rachel, what's going on that's difficult, that makes this question a little bit more difficult?
So both values are greater than the mean.
Right. So we're saying, we're looking at some portion of the curve that's falling sort of above, right? And so how might we go through and figure this out?
If you calculate the z-score for both,
And if we do that, we get, this is about 0.60, and this is about 1.60.
okay, and then if you take the mean to z, or the mean to z for 0.6, and then the mean to z for 1.6, and subtract that.
Absolutely, you're so smart. Right? So we get, for 1.60, probability is 0.4452. And for 0.6, it was 0.2257. And so we get a final answer of 0.2195. So we have about, and thinking back through that this, so this isn't just a fun numbers game, right? What we're looking at is we're saying, literally, based on our evidence for this highway data, we've got about a 22% life probability of grabbing someone driving between 65 and 75 miles an hour as they pass through this portion of the road. But again, with these types of things, wanting to make sure that you're sort of plotting this out and saying, all right, how do I go through and mathematically capture this specific region of the curve that we're looking for? Okay. Questions about this? Okay. Expected specific probabilities, SAT scores, right? 500 to 100. What's the minimum score necessary to be in the top 15% of the distribution? Again, not to belabor this too much, but we're going to go through top 15% of the distribution. We're going to go through, and so we're going to look at our Z chart, and we're going to say what's the top 15%, what falls in that. I got a Z-score of about 1.04. And so then I've got a Z of 1.04, I've got the mean, and I've got the standard deviation, is then just working through back things and finding what that actual value is going to be, right? So I need to find an SAT score that's exactly 1.04 standard deviations above the mean. Now, if I take 1.04 standard deviations divided by the standard deviation, that's 104. Add 104 to the mean, 500, I get a mean score or a value of 604. Okay? So, and then going back through and saying approximately 15% of the population will have a score of 604 or above, and then could go through and say whatever, 95% of the population or 85% of the population will have a value of 6.04 below. What are the values, range of values to define the middle 80% of SAT scores? Again, if we go through, take that distribution, Zach, what are we looking for in terms of Z scores? If we're looking for the middle 80%, you can just tell me in general, you don't have to actually spend time looking through that.
Right. Let's see if we have a value that shows us what would be the top 20%. I can't remember.
Okay, so, yeah, or go through and take it, so if we're looking at the middle 80%, right, the middle 80% of the distribution, what's the proportion that we're looking for on either side of that middle 80%?
40%.
40% on either side, right? So we would go through, take a look at our Z-score table and say, all right, what Z's value gives me 40% of the distribution between that benchmark and the center, right? And then it's just plus or minus. If you go through and look, it's about Z equal 1.28, right? And then we can go through and take that Z-score 1.28 times a standard deviation of 100, 128. So 500 plus 128, 500 minus 128, we get a range. So SAT scores between 372 and 628 is going to capture the middle 80% of that distribution. People feeling comfortable with this, I mean, or at least being able to sit down and be able to work through these problems and be able to figure this out. Again, it's a lot of just sort of graphing and math and sort of going back and forth between your values and Z distributions and things along those lines. Just make sure you're going through, double checking your work, and that the values that you're getting actually look like they could be reasonable estimates based on your graphs that you plotted out. All right. So again, why is this important? Like, why do we care, aside from just this is something that we're doing for the whole heck of it, right? Again, this idea that our distributions and corresponding probabilities, this is really the entire basis of our statistical inferential statistics, at least the frequentist statistics that we most commonly use, okay? We've utilized normal distribution here, but for different types of test statistics. These test statistics have hypothetical distributions that are known, right? So we've got a t distribution, and we know that a t distribution, depending on sample size, under a null hypothesis, sort of follow t-scores. If you infinitely ran something again and again and again and again, you would find a distribution of t-scores. Say, like really actually in the population, these two populations, the mean of the population is 0, right? And that's a fact. But if we go through and we randomly sample from this population, sometimes we're going to get means that are higher, higher, higher. Sometimes we're going to get stuff lower, lower, lower. But as the farther away we get from that mean value, the less likelihood that value is going to occur, right? And so, based on some mathematical properties and statistical stuff, I'm not going to make you derive and prove distributions and things like that. But what we have is a known distribution for given degrees of freedom for t. Same thing for our F distributions, chi-square distributions. These are all statistics that follow a known distribution of scores. And so if we go through and we find a statistic and we test against our null hypothesis, so we're saying, assuming that the mean of this population is actually 0, what's the likelihood that I would obtain a score of this value or higher, assuming the null hypothesis, right? And so this is where we can start to go through, derive p-values and our test statistics and things along those lines. So, but knowing this and not just sort of taking your z-scores and your t-tables and things like that at face value will give you a better understanding of this stuff, and also help you as you start to transition even more advanced statistical analyses, or things that start to say, well, you can't do this because the distribution of that statistic is unknown, right? Well, if the distribution of that statistic is unknown, then we don't have a value here, so we can't derive an exact probability out of that if we don't actually know what that distribution looks like, right? Starts to provide better and more full meaning if you kind of understand some of the basics of this than saying, oh, well, I know that's what this says, but I'm going to ignore that and pretend it's not a real thing, right? It actually is a real thing and can be quite severe depending on the level of bias and things like that. Okay. Questions on distributions, anything like that we've covered up to this point? All right, let's take a break. You guys are champions. All right, folks. Feeling comfortable with the z-scores, and again, we moved through that pretty quickly, but sort of a rehash of undergraduate statistics and things along those lines. If you have questions, track me down. Happy to provide additional clarification, things like that. Okay. But what I really want to focus on and spend the rest of the class talking about is some confidence intervals. Okay. So at this point, all of our descriptive statistics that we've calculated for our corresponding population parameters are just sort of means, right? We've been calculating mean, standard deviations, things like that. But essential, always to recognize that reported estimates are an approximation, right? It's our best guess. But likelihood of having our sample statistic exactly meet our population parameter approaches 0, right? As our sample size increases, Sort of the differences gets, on average, gets smaller and smaller and smaller, but it's never gonna be 100%, right? So what we need to do, or what would be useful, is have some additional measure of precision, right? So this is my point estimate, this is my best guess, right? If you put a gun to my head and ask me what my best guess is, the mean's still gonna be my best guess, right? But if you start to ask me how precise I think that estimate is, that might start to change depending on some circumstances, right? And so this is where our interval estimates come in. Our interval estimates, as you've probably picked up from some of the readings that we've assigned at this point, providing both an index of the precision of our estimates, as well as range of plausible values for a population parameter based on the available data, okay? Like anything else, your statistics are only as good as your methods, right? If I have crappy methods, then my interval estimates, my point estimates, all that stuff probably aren't that good, right? So again, it's an important caveat that you always want to keep in your mind, that when we're providing these interval estimates, it's always based on these data. Given the data that we have, this is what we would expect to be plausible range of values for this actual parameter, okay? So for example, we say, research suggests people who exercise 5 hours or more a week live longer than the average US citizen. How long do individuals who exercise 5 hours a week or more typically live, okay? So this first part says, this is our statistical test, says, yeah, we have a reliable difference between people who exercise and don't, and people who exercise who live longer, right? Well, that's fine, but how much? By how much longer, right? That seems like an important thing to know, right? I mean, is it 10 minutes? Because I don't know, it's 5 hours a week or more, that's an investment of my time, right? Like, is it worth it, right? How much of a difference are we expecting? Also, difference in height between males and females is not 0, right? And if we did a statistical test and we said, here's our men, here's our women, yep, their average height, the difference in their average height is not 0, right? Well, how much of a difference is there, right? These are the types of things that we get with our interval estimates. Our confidence interval is an interval estimate that we create based on some pre-identified level of precision. Okay. Components, we've got our point estimate, we've got our confidence level, and then we have our interval estimate here. Okay. And again, probably not news to anybody, I have seen this before, just wanting to get you guys thinking very critically about what's going on with these interval estimates. Okay. So now, formal interpretation of our confidence interval. The technical statistical interpretation of this is, so if we had an infinite number of replications of the same size growing from the same population, this interval, or our confidence, or the proportion, our confidence level is a proportion of intervals expected to capture, is the number of intervals that we would create hypothetically that would actually capture that true population value. What you often see people is saying that there's a 95% chance that the confidence interval contains the true population parameter, okay? You see this all the time, right? And in the readings they say this isn't correct, and some people get more worked up about it over other people, but if we know it's not correct, we would like it to be correct because it's sort of easy to understand, but it's actually technically not what's going on. And what happens is we start to get a false sense of assuredness in terms of our statistical procedures and things along those lines. The problem with this, right, the reason that this is incorrect, when we're saying a 95% chance that the confidence interval contains the true parameter. So I go through, I do my study, and I say, all right, there's a 95% chance that this interval that I've created captures the population parameter. Issue is that our inferential statistics and the stuff that we do, almost all of it here, is a frequentist approach to estimation, right? What these statistics are assuming is that we will create an infinite number of, or all the possible samples that could be drawn from this population of a certain sample size. We're going to do this again and again and again and again. And if we do this again and again and again and again, think about if, again, let's just use height, the mean height of students on Wyoming campus, right? And I'm collecting samples of 100, right? there are, I don't know how many students on campus, but the number of samples that I could collect of size 100 with replacement and going through and doing that, it's a big number. It's a really big number, right? And every time I would do that, the confidence interval around that mean estimate of height is going to change from study to study. Or think about this as you do your thesis, but then somebody else replicates your thesis exactly, drawn from the same population of people over and over and over again. Your confidence intervals are going to jump around, right? And what you see, and is demonstrated in this very nice graph by Cumberland Fitch, is that if this is the actual value, if this is our true population parameter, right? If we go through, we see that most of these intervals capture that population parameter, right? But some of them don't. Here we've got 2 of these interval estimates that don't actually cover the parameter that we're actually interested in capturing, right? Now this isn't to say these are bad studies. These are probably fine studies, but just on average, every once in a while, you're gonna get a sample that's just kind of weird, and it's just gonna fall outside the bounds, right? So we see that some of these intervals capture the replications, and sometimes they don't, okay? So when we claim that there's a 95% chance that any one of these intervals capture the population parameter, what we're doing is we're assuming that the population parameter is a variable, right? And the frequency at which any one of these given interval estimates grabs up and covers what you're actually trying to measure, it's either 0 or 1, right? It doesn't matter how many times you get this interval right here. This interval will never capture the population parameter. So there's not a 95% chance that this interval from here to here captures the population parameter. It doesn't matter how many times you do it. The amount of times that that interval is able to grab includes your true population parameter is 0, right? Same thing with these, it's always going to capture it, right? If I have an interval from here to here, there's a 100% probability that it's going to have it, right? This one has a 0% chance of grabbing it, right? And so when we say there's a 95% chance that this interval that I've created here, this one right here, contains the population, the actual population value, it implies that my population value is jumping around. And sometimes this interval will, like 95% of the time, my population parameter is going to fall in this interval, and 5% is not, right? And that's incorrect, right? Again, it's something that we see and people talk about a lot, but what we're ignoring with this is this idea that when we calculate a confidence interval, it's this idea that 95% of the possible, of all possible intervals that could be calculated will capture the population parameter, not this specific one, okay? And so it's kind of tricky, but sit down, think about it. People kind of understand sort of the discrepancy, what's going on. It's very subtle, but it's one of these things, again, it's noted in some of our readings that it's just perpetuated, and then pretty soon we have things like these confidence intervals starting to be used to make very, very big and life or death decisions, like is this person's IQ below a certain point that would qualify them for execution or something like that, right? Or if you say, well, 95% of the time that this person is intellectual, has an intellectual disability, not 95, like the person either does or they don't, right? It's just wanting to look at the precision of this given estimate. People sort of see why this is problematic to say, oh, 95% of the time my population parameter will fall within this interval. Okay. Neiman, so this is Greenland, Psyc Neiman in this. Coverage probability is a property of a long sequence of confidence intervals captured from valid models rather than the property of any single confidence interval. This is what's frustrating with statistics. Our statistics, our data that we get is just one of an infinite number of possible responses that could be collected from this data, right? There's no way to know whether or not we've got one of these intervals or one of those intervals. I mean, there is. We just keep doing the study over and over and over and over again and start to get a sense, right? But a couple of things to keep in mind. One, there's no way to know which one of these ones we are based on a given study. And two, seeing that sort of this property of long sequence of confidence intervals computed from valid models, right? Now, if you don't have valid measures or your methods suck, it doesn't matter how many times that you go through and make this estimate. It's there's a possibility, and you would never know this, that 0% of your confidence intervals will ever actually capture the true parameter because your methods are awful, right? So again, thinking about this from conceptually, or from computed from valid models. And this is where the methods meets up with the statistics. Again, you can't fix the numbers of your study if your study's awful, right? If your study isn't measuring exactly what you think it's measuring, or your measures are all over the place and things like that, your data might look poor, but it could be that your data is way off in left field, playing a completely different game than you want it to play, right? It's uncomfortable to think about this, but very, very important. As you're designing research, evaluating research, number one question should be, okay, this is what they say they want to do. Is what they're doing actually map onto anything that might even approximate what they're trying to get, okay? Once we've made that decision, then we can talk about the statistics and some of the precision and things like that, but something that's important to remember. Again, these are the types of caveats, again, in these readings talking about, so yes, this is the statistical model, and this is how we can interpret p-values and things along those lines, assuming that all of your assumptions are accurate. Are all of your assumptions accurate? No, never, ever, ever, right? And so our confidence just starts to it keeps going down and down and down, that what we're detecting actually get into everything. So that's why we're looking for convergent evidence to try and sort of supplement those test statistics, sort of methodological evaluations and things like that, to try and get a sense for sort of, are we kind of circling the landing strip, or are we way off in the ocean somewhere? Yeah.
So why is it that we use a 95% confidence interval instead of a 99? Because wouldn't 99 be better if we're, really trying to capture what the actual population parameter is?
What happens when we jump from a 95 to a 99% confidence interval? What does it do? What's that?
Makes it harder to detect significance, I guess?
Uh, It can. Do our confidence intervals get larger or shorter when we go jump from 95 to 99?
Shorter?
What do you think, Rachel?
Larger.
Larger, right? I can give you a 100% confidence interval on the average age of the U.S. population. It's somewhere between 0 and 250. So the mean, that's all, I can tell you with 100% confidence that the mean age of U.S. citizens is somewhere between 0 and 250 years old, right? 100%. And I would bet anything that I own that is accurate, right? And so what happens is our confidence intervals start to increase, they tend to get larger. Now, as our sample sizes start to get, primary determinant of the width of our confidence intervals is our sample size. As our sample size goes up, we get much, much more precise estimates, and so our error starts to shrink down, right?
Okay.
Now, why is it a 95% confidence interval? Sort of corresponds to our p-value of 0.05, right? So it's just convention, but there's nothing to say that you couldn't use other types of confidence intervals, and for certain types of statistics, you'll see people using intervals like 90% intervals, and we'll talk about down the road why we would do that, right? But if I want to be really, really sure, right? If I want to be really precise, I can bump it up to 99, and then say, like, if I'm saying this is sort of some method, sort of this proportion of at this score above, this is where you're cheating, right? Or you need some sort of invasive surgery or something along those lines. I might not be happy with 95%, right? I want to be very, very sure that I've got 99%, right? And so wanting to go through and capture sort of everybody who could be coming through with that. Questions? All right. So, valid interpretations, not the 95% chance that my interval captures the population mean. Pulled these from that Cumming and Fitch article. Confidence intervals represent a range of plausible values for the mean given the available data. Again, given the available data, right? I'm just saying, based on the data I have, these are plausible values for the actual population parameter. Now, if my data aren't any good, then that's sort of, we're talking about a whole nother thing, right? But given the data that I have, these are the range of reasonable values that could cover the actual population parameter. Values found falling outside this interval are relatively implausible. Not impossible, right? It could be. It's just given these data, it's implausible that our whatever statistic is or whatever parameter it is that we're trying to estimate would fall beyond these bounds. Okay? So range of plausible values, I like that one. Coming and Fitch like that one. I think it's a good way to think about things. It's conceptually more meaningful, right? Because we're saying, so here's my point estimate, here's my best guess, but reasonable values for this based on my data could range anywhere from this to that. The observed data are compatible for values of the mean falling within the interval, but relatively incompatible with values falling outside the interval. This one's kind of nice too, right? So any value that falls within this interval is compatible with the data, right? We would say reasonably compatible with the data. Like you could say, oh, well, I say the mean is 50. You'd say, well, could it be 55? Like, yeah, it could be 55, right? It's within that interval, right? Stuff that's outside it, is the mean 30? Well, probably not. It could be, right? Based on these data, I would say 30 is an implausible value or not a reasonable estimate for the true population parameter. So we like this one. Here, lower limit of the interval provides a reasonable lower bound estimate of the parameter. Upper limit is a reasonable upper bound based on these data, right? So really this is about the upper limit of what we would have guessed that the population parameter might be. This is really the lower bound of what we might have it be, like that one. Margin of error reflects the largest area of estimation likely to be made based on these data. This is a little bit different, right? These ones are talking about here are upper lower bounds. Here you're taking the margin of error that you're calculating, right? That's the plus or minus that you go on the mean, and saying the largest, the greatest amount of error we're likely to have made is plus or minus 2 points given these data, right? Again, depending on the context, that can kind of meaningful, right? So I can say, I would say average, my best guess is average value or average income of American family is lower than it should be, $35,000 a year or something like that. Okay, and so I'm pretty reasonable that we're got that within, say, plus or minus $7,000 a year or something like that, right? So you're identifying your sort of margin of error there, like that. We can be 95% confident that our interval includes the mean. So this is a slight derivation of the previous one. Coming and Fitch put that in. I don't like that. Okay, and you could do it, but let's not. All right, because this is what happens when I'm asking you guys to use this. Is people will just say, like, we're 95% confident that our interval contains population. Don't do that, right? Because again, it's not like this is much more meaningful. It's just like this. Fine, whatever. Like, but if you can tell me what that means, like if you can actually give me a definition for it, then fine, you can go ahead and use it. But it's just going to be easier to actually think about what we're trying to measure, the level of precision that we have on that estimate, and then talking about upper, lower limits, things along those lines. Okay. Researcher who routinely reports 95% confidence intervals can be expected over a lifetime. About 95% of those intervals will capture the parameters estimated. Right. So, if you, from here to the day that you leave this earth, consistently report 95% confidence intervals, if we go back through and look, about 95% of your intervals probably did capture the parameter of interest, and somewhere about 5% probably didn't, right? Trick is we never know, right? We don't know if we did or not unless we just want to do studies over and over and over again. And so always wanted to say, based on the data that we have, right, this is our reasonable estimates for upper and lower bounds for whatever it is that we're trying to estimate. Questions on this? Okay. Strengths of interval estimation. With our interval estimates, with our confidence intervals, we're getting both a point estimate, our best guess, okay, and our estimate of probable error in that prediction. How accurate are we? Why do you think we maybe are hesitant oftentimes to report our confidence intervals? If we're being real, if we're doing real talk, among scientists, yeah.
It makes it less concrete if you've got, so if you can show like this range, and you're like, we don't know exactly what
Yeah.
it is.
And what's often a property of that range? It's usually, oftentimes it's very large, right? Basically, we've got crap estimates of stuff, right? I can say, I think on average, I think people will tend to score, 50 points better than these people, but it could be anywhere from 10 points to 150 points. All right, as long as it's not a 0-point value, I can claim statistical significance, but sort of my difference between these might be anywhere from something that has no practical meaning to something that's huge, like just grossly huge and enormous, more than what I've got, right? As long as that interval estimate doesn't capture 0, we can claim statistical significance. But the size of that interval might be like this, and we don't like to think about that, right? And so it's uncomfortable sometimes. But in terms of conveying sort of what we know, we're sort of saying, how much? By how much could this be? This will quickly come up when we start calculating confidence intervals on effect sizes. Confidence intervals on effect sizes are notoriously larger than confidence intervals around means and things like that because of the distribution of effects. And so you'll say, so I found a large or a medium effect of D equals 0.5, but the confidence interval around that effect size could be anywhere from 0.03 to 1.6 or something like that, right? I'm more comfortable. I like saying, it's about a medium effect, right? But it could be anywhere in this huge area, right? But it's important and responsible that we let people know sort of this is kind of the range that we're looking at. So again, how much is generally more useful information than is at 0, right? Again, thinking about in terms of screening, right? In terms of skew or kurtosis, right? I have significant skew. Well, if you say you have significant skew, what does that mean? Okay. Maybe not. For the statistical testing, we've talked about this. So if I run the statistics and I say that I've got the skew value of my measurement is statistically significant, and as a consequence, I have statistically significant skew in my data. What does that actually mean?
It's basically not overtly like centrally located.
Getting closer, but not quite. Anytime we're running a hypothesis test, and this is just something good to keep in your mind, anytime you're running a hypothesis test, almost always what you're doing is saying, is this value 0, right? That's almost always, or is this different 0? Is some value 0? Now we could change our hypothesis test to do something more interesting than that, but typically, standardly, what we're doing is just saying, is it 0? So if I say, I have statistically significant skew in my data, all that's saying is the skew value of these data is something that's different than 0. Okay. Now, depending on so my skew value might be 0.2, right? Are we generally worried about distribution with a skew value of 0.2? No, right? But if I say it's statistically significant, that makes it sound like it's a lot worse than it is, right? That there's some anomaly in these data, or that it's not going to be useful for doing things. All this is saying, I don't care if it's 0. My assumption isn't that it's 0, right? It's just something that approximates normality, right? And so the question of how much is a much more interesting question than is it 0. And this starts to get into sort of this idea of effect size and things like that. With our confidence interval, if I went through and I said, all right, not is my skew 0, but what is my skew? Well, I've got a value of 0.3 that could range anywhere from 0.8 to negative 0.1. But okay, well, that statistical test is going to say it's, say if it's 0.1 to like 1.3 or something like that, right? It's going to say it's statistically reliable, but even at the upper end, that's still within the bounds of sort of what I'm not going to be concerned with, right? And so a nice example of starting to use these interval estimates to say how much of it is there, as opposed to is it equal to 0. Okay? So our interval estimates basically can be substituted in terms of hypotheses tests if we wanted to use them this way, okay? So if our 95% confidence interval contains some reference value, typically 0, right? We would interpret this as evidence for evidence failure to reject the null hypothesis, right? Basically, we're saying that 0, a difference of 0 or a mean of 0, is a reasonable value given these data. this corresponds directly to a p-value of greater than 0.05. If it doesn't contain 0, then we can say, you know, we would reject the null hypothesis and say that 0 is not a reasonable value based on these data, right? So again, if our doesn't and again, not evidence for the null effect, scratch that out, that's me sort of not saying things correctly. So we were just saying that we would fail to reject the null hypothesis, right? We would say that these data are not inconsistent with the null hypothesis, right? I would get my hand slapped here because I've suggested that something is evidence for the null. That's not what we're doing with this, right? But if that interval doesn't capture some population parameter or some value, we can say that this is evidence for statistical significance. Now the thing here, and this is where people get turned around sometimes, and you see this when people are trying to work together their problem sets, and so we'll do like a t-test or something like that. We'll say statistical test, t-test follows a t-value of 3. We reject the null hypotheses, given a p-value of p less than something, or given the exact p-value. Subsequent examination of the confidence interval provides further evidence for rejection of the null because confidence interval doesn't contain 0. Okay, what's wrong with that statement? Does your confidence interval provide further evidence? Or is it just a restatement of the evidence you already found, right? Based on the stuff that we're going to do, your confidence interval is going to be calculated from the same damn scores that you calculated your test statistic with. And so it's physically impossible. By definition, if it's impossible to calculate a confidence interval that contains your null value, and then you get a t-test that doesn't, right? And so, and this is just like people are trying to sort of work in this idea of a confidence interval, but your confidence interval, your p-value doesn't give you anything that you don't already get with your null hypothesis or your confidence interval aside from just that specific p-value, okay? In terms of if you want to make an up-down decision on whether or not we fail to reject the null hypothesis, no new information there, right? So to say that your confidence interval confirms or refutes what you obtain for your statistical test is actually not, it can't, like unless you calculate it wrong, these always have to be the exact same thing, right? So it's not as though our interval estimate gives us sort of further confirms what we already decided based on the hypothesis test. It's just giving us more information in terms of how precise our estimate is, range of reasonable values or unrefuted values within sort of that interval, stuff along those lines. So don't make that decision or that mistake if you're trying to incorporate your confidence interval and say, oh, so I was able to reject the null hypothesis with my test, and then if I look at confidence interval, I get further evidence that I made the right decision, because it's all made from the same numbers. All the same numbers go into both of these. It's just your confidence interval gives you more that information on the reject, fail to reject, and more. Okay. Yeah.
More like helps explain their decision kind of thing instead of.
Not necessarily helps explain the decision. It just gives you a better sense for, instead of just saying making yes/no decisions about is this 0 or is it not? Do I have evidence to claim a statistically significant difference or not? What we get with this is a sort of a range for what this actual parameter is, right? So if I'm wanting to see if I give jury instructions, right, and I'm going to change my jury instructions, and I want to see if it has an impact on rates of guilty, not guilty, right? I can run my statistical test, and what my statistical test is going to tell us is whether or not that those new instructions had a reliable effect on their behavior, right? And you say they do, and you say, and we see that there's less guilty, right? That's fine, and that's interesting. What's actually more interesting is how much, right? Like how much, so if I give these instructions to juries, like what's the likely impact on rates of guilty verdicts, right? Because if you just say it increases, I don't know, it might be 100% increase, or it might be a 2% increase depending on how big our sample is, right? But if I go through and I give you an interval estimate on sort of what that difference is, I can say, well, we would expect anywhere from a 15 to a 25% increase in the number of not guilty verdicts based on this, right? I think that's a lot more interesting than just saying, yeah, this has an effect at p less than 0.05, right? And this is where we can start to work in your interval estimates on things to actually sort of draw in sort of meaningful discussion about not just is there a reliable effect, but the size of that effect and some of the differences you can expect. Questions? All right. Provides a more meaningful and accurate perspective on effects of the literature. Right? This is where we are going to start looking at, okay, my mean that I found in my study is a mean of 50. Or let's say that I find a correlation between two variables in my study is a correlation of 0.2, right? But all these other studies, someone else's study that I really wanted to replicate, they found this correlation of 0.5. My correlation of 0.2 is considerably lower than their correlation of 0.5. Did I fail? And maybe even like my correlation of 0.2 doesn't actually even reach statistical significance, right? Maybe I've got a non-significant correlation of 0.2, whereas the study that I was hoping to replicate had a correlation of 0.5, right? Now, are my data inconsistent with that other study? I don't know. It's tough to tell, right? But if I had a meta-analysis that had looked at all the studies that had done this, and they say, okay, so Trent found a correlation of 0.5, but his estimate is actually quite a bit larger than what we typically see in the literature. Typically, we see something about 0.35 or something along those lines. Here's the interval, the estimate, the confidence interval around sort of this aggregate across studies for what we should expect in the actual population. Maybe my correlation of 0.2 is actually sort of falling within that confidence interval. So based on the existing literature, my value that I found is actually not inconsistent. It's actually kind of right where we might expect, maybe on the lower end, right? But this helps as you're going through and interpreting your data, because otherwise you're just sitting there with a single study with a correlation of 0.2 and non-significant effects, and you're feeling dejected and sort of sad about the whole thing, right? But if you're savvy, you can go through and take a look and say, well, we didn't find a statistically reliable effect in the correlation of 0.2, but how do we get a correlation of 0.2 to be statistically significant? Are correlations of 0.2 always not significant? No, they regularly are, right? If so this is my point estimate, and I just get a bigger sample size, they'll very quickly become statistically reliable, right? So what I can say is, well, with this study, sort of limited its power because I wasn't able to collect a large sample. However, the point estimate of my effect falls within the range of what we would expect from sort of the larger literature, and so sort of we still can't say yes or no, but it looks like at least this is not nothing, right? And that's a much more satisfying interpretation than, can't say yes or no, it's tough to tell. I guess we'll have to, I can't reject the null hypothesis based on this, but so going through, taking a look and thinking about these interval estimates, putting your own research within the context of other literature, particularly if for practical reasons you don't have the resources to go through and collect 500 people, right? You can make a very strong, compelling case for saying, yeah, well, looks like we have a relationship that I can't say within this specific study is not reliably different than zero, but my point estimate is falling within the range of what we'd expect given the larger literature. And so I'm going to say this is a real thing and not a real thing, and then move forward. You can hail. Okay. So people understand sort of some of the stuff we're talking about here? Okay, cool. From Wilkinson, inclusion of confidence intervals for estimates of parameters, for function of parameters, such as difference in means or effect sizes, can be extremely effective way of reporting results. Confidence intervals combine information on location and precision. They are, in general, the best reporting strategy. At some point, I thought like Batman was maybe giving us that. I'm not sure why that. But very, very important as we move through. I want your confidence intervals not to just be something that's tacked on as you're discussing problem sets in here. I want you to be get practice at actively using these as a meaningful thing, not just, I rejected the null based on my p-value, and also the confidence interval supported my decision to reject. That's sort of, right? And sort of mixing up some of your interpretation, thinking about the context and the study and the data. Sort of how do I interpret this confidence interval in a way that's meaningful given the data, as opposed to just your plug and play plausible values for this parameter fall between x and y. I mean, that's fine, but I want you guys to be thinking with this, looking at it, and I will be looking for this. I will constantly looking for this in your sets, okay? So really gonna push for, I got a whole new, with that ASA statement, sort of, we're on the front edge, we're in the vanguard of forcing you guys into responsible statistical analyses, so I'm gonna be looking for that. So make sure you do that. If you report some effect and you haven't reported a confidence interval and later on an effect size, you should be anticipating losing points on that because you haven't sort of done everything that you can. Okay. Also tests will be watching and maybe staying possibly. Okay. Calculation of confidence interval. 3 pieces of information. We've got the sample mean, standard error, and then the z-value later on, the t-value for corresponding to chosen level of precision. Standard error, very important. We're going to talk about more about this next week. Standard error gives you an estimate of how much difference, right? How much error is expected from one replication to the next, okay? It's a measure of variability in terms of replications as opposed to your given data set, okay? How well is this individual mean that I've calculated right here and now expected to estimate that actual population mean, right? So if I do this again and again and again and again, over sort of different replications, how much should I expect my mean estimate to jump around, right? Or alternatively, how close should I expect this mean that I've calculated to be to my actual population parameter? Okay? So we want big standard errors or small standard errors? Small standard errors. And what happens when we start talking about bias in our standard errors? Why is that bad? What do you think, Candace?
I said it increases standard error.
Right. And so if we have larger standard errors, why are we concerned? What is that? Why might we be concerned about with our statistical analyses?
Because then the statistic is less likely to be close to the population parameter.
Right. It impacts our inference, right? So if I have systematically lower standard errors than I should have, and your standard error is almost always going to be in the denominator of test statistic, right? So the denominator of my test statistic is smaller. What's that going to do to my test statistic? Make it bigger or larger? Or bigger or smaller? If I have a smaller denominator in a ratio, what does it do with that ratio? Makes it go up, right? So if my standard errors are systematically smaller than they should be, my test statistics are always going to be larger than they should be, and I'm going to be saying that there are things there at a greater rate than I should be, right? Same thing if I have inflated standard errors, what's that going to do to my test statistic? Drive it down, right? My test statistic is going to be lower than I would expect it to be, or it's anticipated to be based on the procedure that I'm using, and so more often than not than I should be, I'm going to be failing to reject the null hypothesis when I probably should, right? Standard error is incredibly important. Primary influences on standard error. Hisham, what are primary influences on standard error? Looking at this equation. Your sample size, right? Your sample size, and to a lesser extent, your standard deviation, right? But your sample size is the big one, right? As your sample size goes up, what happens to your standard error? It goes down, right? We get more and more precise estimates, we get less error, we get less of a difference from one replication to the next as our sample size goes up based on its influence on our standard error. Okay? So again, essential for the calculation of our inferential statistics. Really want you guys to be understanding sort of what is going on with standard error. We'll talk about this a little bit more on Wednesday, next Wednesday. Okay. So, confidence intervals, we got our mean, our standard error. Standard error we can take, these are equivalent. Our standard error can be standard deviation over the square root of n, or right? Those two are equivalent functions, okay? Doesn't matter which one you're using, right? If you get variance, you just square the whole thing. If you get standard deviation, you take that over the square root, and just making sure that you're not. Because if you take the variance over the square root of your sample size, your estimate of standard error is going to be abnormally large, and it's going to have negative impacts on your intervals and things like that, okay? Formula, our 95% confidence interval is just our mean, plus or minus our z-value times our standard error. As we get into other stuff, we'll be using our t-statistic, 90, 95, and 99% confidence intervals. These are all standard values here. So, I'm going to go through and run a couple of examples. So we've got former librarian and a local library claim that on average books are 20 years old. So it's like, all right, books in this library are about 20 years old. New librarian, new hotshot kid comes in, and he says, I don't know about you, old man. I think your estimate of the age of books, because this is beef that librarians often have, is different, right? So what he does is he goes through, randomly selects 150 books, records the publication date, right? Mean age of the books in the sample is 23.8 years with a variance of 67.5, okay? So what we want to do is a couple of things. First of all, we want to calculate the point estimate for the age of our books. Rachel, what's our point estimate for the true age of this population library books? Yeah, 23.8, right? It's our mean, right? Based on our data, that's our best guess for what the population mean is, right? Old guy says it's 20. Based on these data that we've got, our best estimate is 23.8 years, right? So what we want to do now is create a 95% confidence interval for the true age of these books, right? So we've got mean 23.8, our standard deviation, or is that our variance? It's our variance. Variance is 67.5, and our sample 150. Okay. What's the first thing we need to do, Sean?
Calculate the standard deviation.
Okay. We could do that, but we can just jump straight to standard error, right? We could go through and do that, but in terms of precision, we can just go through and do that, right? So we got standard error equals square root 67.5 over 150 gives us our standard error estimate of 0.671. Okay. Then all we need to do is take our mean estimate, 23.8 plus or minus. Okay, what level of precision are we looking for here, Bijan?
Sorry,
What level of precision are we looking at for a confidence interval? 95, right? And because I know I'll apply our stay with that 0.671, it gives us 95% CI of 22.48, 25.12. Pretty easy, simple stuff, not terribly difficult, but this is just standard estimation of a confidence interval around that mean. Okay, people sort of comfortable with that? See how we got that? Okay, now what we want to do, provide an interpretation of the confidence interval. Tess, can you give me a interpretation of the confidence interval?
Oh man, so I guess like given the data, like a range of plausible values, you would expect to contain like the age of the average age of the books in the library would be like 22.48 to 25.12.
Right, perfect, right? So based on these data, right, we would say that our best guess, so we would guess that the average age of books in this library about 23.8 years, right? However, plausible estimates for the true age of the books in the library. Again, because what's our population? All the books in the library, right? We don't want to go through and register all, or take a look at all the books in the library. So, but our best guess is that that true value, if we were to go through and do that, based on these data, anything from 22 and a half to a little over 25 years would be reasonable estimates for the actual age of that book. Okay. Some things, and so again, that's sort of the literal upper thing you're talking about, upper and lower bounds, but things wanting you guys to think about as you're making these interpretations. Number one thing, start looking at the precision of your estimate, right? So here, so we've got anywhere from 22 and a half to about 25 years. That's pretty reasonable, right? So I mean, I might comment and say, confidence interval suggests a reasonable level of precision in the estimate of the age of books, right? That's important, right? Or you could start out saying, it looks like my estimate's crap, so it's huge, so you got tons of error in this, but this is my best guess, right? Here, I might highlight that it looks like we have a pretty precise estimate. We could say based on these data, plausible estimates for the average age of these books in the library, anywhere from 22 and a half, 25.1 years, right? Or we could start, again, focusing on the precision of our estimate. We could say the largest error of estimation likely for the books made in this data, based on these data, is around 16 months, okay? So if we go through and we take 1.96 plus or minus 6.71, we get a margin of error of plus or minus 2, about 1.3, okay? So our average, our expected error, our maximum error in our calculation of the true age of these books is plus or minus 1.3 years, right? Or if we switch that over, we can say, 16 months, about 16 months is about our expected error on this stuff. So all of these things together, now, if we were to run a hypothesis test, and we would do, this would be a one sample t-test, what would we say about the original librarian's estimate that books are, the average age of books is 20 years? Can you tell me we like that? So based on our interval estimate, the old librarian says books are about 20 years old, right? Is that a reasonable estimate given the data that we've collected? No, and why not?
Because the 20 years is not including the CI.
Exactly, right? So we've got our confidence interval that doesn't capture sort of this estimate, and so we would say that an estimate of 20 years old is not compatible with these data. These aren't compatible. These data aren't compatible with an estimate of 20 years, right? Anything from 22 and a half to 25.1, kind of, right? And we've got a pretty good estimate of sort of where we're at on this, right? So if we were to run a t-test, a one sample t-test, would we reject the null hypothesis or would we fail to reject the null hypothesis? Gabby?
Fail to reject?
What's that?
Fail to reject one of these? Or,
Fail to reject says that we didn't detect a reliable difference.
oh, we reject.
We would reject the null hypothesis, right? And so we don't even have to do a t-test. We can just say, yeah, I know that t-test is going to be, we're going to reject the null hypothesis at alpha 0.05, right? If you're really hard up and need to see a p-value, I can do that for you, but we don't need to, right? We've already found that that point estimate, that reference value doesn't fall within here, and so we can safely say that we would reject that null hypothesis. So again, talking about sort of making an estimate in terms of precision, and this is easier because we're working with years, right? We all know what years are. Years have intrinsic meaning to us, and so given this, we can say, yeah, plus or minus a little over a year, we're pretty good in terms of our estimate, right? As you get into arbitrary scales, it gets a little more difficult, but you can start to look at the width of that estimate. If we're all over the place, we're like, yeah, our estimates are not precise at all, versus if they're really tight, we can say we've got a pretty good beat on what the likely value is in the population. Okay. Questions about this? So again, just wanting you guys to think very clearly about what we're getting with these estimates and what they mean, okay? Second example here. Examples. Yeah, we got plenty of time. We'll let you guys out early today, gross. I guess, given that I'm a horrible estimate of how much time it takes me to do things, maybe we won't, I don't know, maybe we'll still have carry over next week. It's tough to tell. All right, so we've got a researcher interested in Flynn effect. Would like to know, current average score would be for an IQ test developed in 1980, okay? What's a Flynn effect? Non-psychologists, I'll let you guys off the hook. Psychologists, anybody know what Flynn effect is?
I have no idea.
All right. It's this idea that sort of as IQ tests get older, sort of the mean score on that IQ test, so we norm it in 1980, right? But as so we continue to use that test, the mean of score on that test starts to shift up, right? And we've seen this happen from the invention of intelligence tests, that we have a set of information, and as a population matures, people tend to get better and better on this stuff, right? And so what happens is we can't just go through and give you an IQ test that was developed in the 70s, because you're probably gonna, the norms that test was developed on are no longer applicable to today's society. You're gonna be way better on that, right? So what we're interested here is seeing if we can demonstrate this Flynn effect, right? So we've got an IQ test that was developed in 1980, and an IQ test should have a mean of what? 100, and a standard deviation of 15, right? So what we do is we go through and take this test from 1980, gather up 120 people, and we test them given this test. And we find that people on average had a score of 107, standard deviation of 12, right? Again, population mean on this test in 1980 was 100. So what we want to do, calculate a point estimate for the current population mean on the old test is going to be what, 70? So what's our best guess of today's, the average score of today's population on this old test? If I had to put a gun to your head and I say, tell me right now what your best guess is.
I'd probably pee and then die. I mean, would we,
It's deceptively simple.
I don't like it.
What would be, anybody help her out? What's our best guess? 107, right? Our mean is always our best guess, right? Based on the data that we have, our best guess for what the true population of today's sort of people living right now, if we were to give everybody who's living right now this test that was normed in 1980, my best guess for what that means would be 107, okay? And so what we've got is we've got mean equals 107, standard deviation is 12, and my sample is 120.
Wait, just a quick question.
Yeah.
Maybe I misunderstood what you were asking me, but, so are you saying that our best guess for redoing the test in 1980 is, the mean is 107?
Yep, so we've got this test that was normed, so normed on the population of humans in 1980, right? And in 1980, the average score on this was 100, right? Because that's what we're always trying to do. But if we take that same test that was normed in 1980 and give it to everybody today, what ends up happening is a consequence of this Flynn effect, we get upward drift in terms of the average score. So the average score is no longer 100, it's now 7 points higher, it's 107.
I misunderstood. I was under the impression that they had redone the test. Even
Oh,
though it says
yep.
right there, IQ test developed in 1980. Apparently I can't read, sorry.
No problem. So our mean is 107. We want to calculate 99% confidence interval. So first thing we're going to do, standard error. And here we've got our standard deviation, so we can just go 12 over the square root of 120, right? Making sure, always make sure that you know whether or not you're dealing with your standard deviation or your variance, because that will have huge impacts on your standard error. We get a standard error estimate of 1.095. If we take our mean, 107 plus or minus, all right, what's our value going to be for our 99% confidence or 99% confidence interval? Candace?
2.58.
2.58, right? 2.58. Always want to make sure that you're using the correct value there, because what happens then to our margin of error if we calculate a 95% confidence interval? If we calculate a 95% confidence interval, is our margin of error larger or smaller? What do you think, Sean?
We calculated 95% confidence interval, or amount would be, within the interval would be smaller.
Would be smaller, right? Because 95% confidence interval is 1.96, right? We're less confident, so we can get a narrow interval band, right? Because we're have more tolerance for stuff that's going to fall out. So 2.58, 99% confidence interval. We want to stretch that out to make sure that we have a broader coverage. And so 1.095, right? So our 99% confidence interval, 104.17 to 109.83. So if this is our interval estimate, Zach, can you give me an interpretation of that interval estimate?
Well, let's see. It's plausible that part of me just wants to say that, yeah, the average score has gone up, but
And you could say that. That would be
Yeah.
part of an interpretation, right? And what evidence would you have that would suggest be consistent with the form effect?
the old average of 100 is not.
Right. So based on these data, right, that original value would be an implausible estimate for the true population value to be now, right? Or these data are not consistent. These data are generally inconsistent with a population mean of 100, just from the fact that it's not included in there, right? We could say, so our point estimate is about 107, but reasonable estimates of population value falling somewhere between 104 and about 110, right? What would we say, Candace, in terms of, are we happy with this estimate in terms of precision?
No.
No? I mean, that's fair. Like, you cannot be happy with it. You have higher standards than I do. I mean, so we're margin of error here. Yeah. Candace is a hard sell. Our margin of error is 2.83, right? So plus or minus on our average, plus or minus a couple of points on this test. Depends on sort of what we're using it for. I would say we're all right, right? As we go through, you'll see confidence intervals that are much larger with margins of error that are much larger than that, right? So in the grand scheme of things, given my old and seasoned wisdom, I would say we're pretty good in terms of estimate. Basically, we're within plus or minus 3 points in terms of closeness, missing the true population value, right? So again, these are the types of things we're wanting you guys to think about, like sort of precision of the estimate, sort of what this means in terms of what we're trying to estimate, right? It looks like, as Zach said, very clear, I would say, evidence that evidence that would support this Flynn hypothesis, right? That we've got an upward drifting of this, right? Now, if we were to have left this on 10 individuals, I think I don't know that we would have clear evidence for this, because what's going to happen to my interval estimate, if I only sampled 10 people instead of 120, what's that going to do to my confidence interval?
Okay.
my confidence interval gonna be bigger or small? It's gonna be pretty big, right? I mean, if I only grab 10 people, I'm gonna say, oh, well, reasonable values or non-refuted values of population mean on this exam today is somewhere between 85 and 130, right? That's not terribly useful, right? But we've got a decent sample, we've got low standard deviation here, and something like that, pretty good. Okay. So go back through, take a look at that, where we're talking about interval estimates and their interpretation, and then wanting to take sort of the actual question at hand and trying to take the information that's contained in that interval and having that be your primary means of interpretation, right? Like your primary sort of basis. We can tack the hypothesis test on later on. We really want you focusing on the effect size and the confidence intervals for that. So we've talked about, like, oh, maybe we'll just eliminate hypothesis testing in here. I don't know if I'm ready for that, right? And that's probably not helpful because you're gonna go out in the world where you have to use hypothesis tests. We're wanting you guys to focus on the interval estimates with this. So, some additional interpretation, if we look at our age of our books, one thing that's important to think about in terms of our interval estimates, based on sort of our method, we're saying that based on the data that we have, this interval that we've collected, reasonable estimates for the age of books are anywhere between, what did we say, about 22 and a half to 25 years. But still, it's important to recognize that our point estimate is still our best estimate, right? Not all of the values within that interval are increasingly likely. As we get closer and closer to those bounds, those become worse and worse estimates of the population value based on the data that we've collected, right? And then we have, just like anything else, we've got some arbitrary cut points where we say, this value is reasonable given the data, and that value is unreasonable given the data, right? So like anything else, we sort of have to take some of that stuff into context, right? Say I'm testing whether or not some value is statistically reliable from 0, and my confidence interval goes from negative 0.01 to 5, right? I've just barely clipped that 0 value right there, just barely, right? I've got a marginal effect, right? Just sort of just say, oh, I reject the null hypothesis. We can get into the same problem with confidence intervals as we would with p-values if we're not being careful, right? But what this does is it says, so that as we get farther away, so those values become less likely estimates. Our point estimate is still always our best guess. Okay? So not all values in our interval are created equal. Same thing with our IQ scores. So this is our range of non-refuted values or reasonable values, plausible values given the data. Things outside of that data are relatively inconsistent with estimates falling outside that interval. But again, it's not sort of uniform across that in terms of likelihood of sort of capturing our population estimate. Okay. We can also, if we wanted to, calculate our point estimate in our estimates in a couple of different samples. Okay. What we have here is we have lectin, chemical found in protein-rich foods. We think might improve memory. Rats, we got a normal diet that contains lectin, and then we got 7 other rats that we give a diet with no lectin. All right, so normal rats giving sort of 10 rats getting normal diets, 7 rats getting a diet where we've stripped all this lectin chemical out. Right? Lectin sample have mean memory scores of 25, variance of 61. No lectin, mean 33, variance of 36 and a half. All right. We're interested in estimating the actual difference in scores across these populations. What I'll do, just for the sake of brevity, most people need me to go through and calculate confidence intervals. For them. But so what's the mean value for our control group? And read this carefully. What do you think, Trevor? For Trent? 33. 33, okay. Is that your control group?
Oh, no, normal diet.
Okay, right, so again, going through and taking a look at this and making sure that you're clear, sorry, I didn't even call you Trevor, this is a different T name.
It's all right, I messed up on the answer, you messed up on my name.
Right. Or even, it's a wash, okay.
Is it 25?
Mean of 25 in our variance,
61.
61, right? And we got a sample of 10 here, right? Our experimental group, we got a mean of what, give me that now? 33, variance,
36.5.
36.5, and a sample of 7, right? Okay, so now, I mean, just as a preview and getting ahead of sort of this process of running these types of tests, even at the very descriptive level, there are things to be gained from this, okay? So we say that lectin should enhance memory, right? Anything that seems sort of off with these data right off the bat? What do you think, Candace?
Yeah, the control group has a lot more variance.
Okay, that's good. Yeah, that's very good. So our rats that are getting normal diet that have lectin, have about twice the variance, well, not quite, but getting close to twice the variance as the experimental group. What else is odd with this? Looking at your hypotheses, what did we expect to happen and then what did happen? Yeah.
So we expected we would expect the experimental group, which would not be to have a lower average.
Okay. Perfect. And this is the thing, it seems like, oh, yeah, sure. But what often happens is people will calculate the statistics and they say, yeah, there's a statistical difference and end of story, right? Well, then it's true. There does end up being a statistical difference, but it's in the opposite direction of what you had anticipated, right? That's kind of a big deal, right? But if you just say there's a difference and don't tell me which way that's going, we can have completely different interpretations of what the hell is going on with this, right? So always sort of reading your question and trying to figure out, all right, what is the hypothesis? Where should this go? And do we see this happening, right? So with our control, we've got an interval estimate, end up with an interval estimate of 20.16, 29.84. Our experimental group, we end up with 28.53, 37.47. Our margin of error here is 4.841. Margin of error here is 4.475. Okay. So, based on these data, what might we pull out from these interval estimates? How's our precision here? What do you think, Gabby?
Compare the intervals, like you could
What's that?
compare your confidence intervals with both groups to see which is bigger and, bigger confidence interval.
Bigger confidence intervals, right? We have far less precision here, right? We've got a difference of, I mean, and we're not working on sort of 100-point scale, right? We've got a pretty big swing, right? If we look at the margin of error relative to our mean, we've got almost 25% increase or decrease, sort of maybe like a 20% increase or decrease in our point estimate, right? So we've got a pretty big swing, right? And why don't we have very precise estimates in this example, Vijay?
Because our sample is too small.
Yeah, our sample is too small, right? And if we've got that small sample, we're gonna have pretty big swings in terms of our interval estimates, right? What about, in terms of, comparing these two groups. We've got some overlap, right, in our confidence interval, but it's not much, right? And what we're likely to find here, now, and it starts to get a little bit difficult, and we'll talk about this in our independent sample t-test. If I look at my experimental group, right, the no electing group, this interval does not contain the point estimate for control, right? And so we might be tempted to say, because our interval estimate here is not compatible with the point estimate of our control group, that this isn't a reasonable value. We have statistically different, that we would say that these groups are different, right? You would be right in your conclusion, but wrong in the reason, okay? Because what happens now, if this was a population value, right? If this was a known population value, we'd be working with something different. But this is also an estimate, right? So we have variability around that estimate. So the estimate of this, for this population mean anywhere from 20, almost 30, between 20 and 30, right? This is about anywhere from 20 and a half. So we do have, so the upper limit of this is captured in the lower, within the lower bound of that, right? So we do have some overlap, right? And what happens when we're running something like this, where we would be looking at an independent samples test, we have to be careful because we're going to have estimates on both sides, right? We're going to have the estimates error, or we're going to have error in both of our estimates. We're going to have error in this estimate. We're going to have error in this estimate. And so what we want to start to do, or what we can do, and this is a very sort of useful thing to go about doing, is starting to take a look at sort of the extent to which these overlap. This is a quote from that Cumming and Fitch article, which is incredibly helpful, where they start talking about confidence intervals, their interpretation, and how, which is based on graphical representations, we can start to say, well, is this group different than that group? Or is this estimate different than that estimate? We're talking about different groups. What we can do is, and so this is a graphical representation, and I've done this, right, because people don't give you the estimates you need, but assuming that they've scaled these correctly, is trying to go through and take a look at upper and lower bounds, right? We compare some, our confidence intervals here. We want to make sure that these are confidence intervals and not error bars. Error bars are tiny, confidence intervals are larger. You should always be reporting confidence intervals on your bar graphs and not your standard error estimates. You'll be compelled, you'll be tempted to report standard error estimates, because why might we want to put standard error estimates instead of confidence intervals? They're smaller. It makes it look like it's more, like we've got more of a difference than we do, right? But let's say these are our confidence interval bars. Making a substantive interpretation of the means, interpret your confidence intervals, and then for independent means, right? So we've got our electing group, our no elective group. If we have an overlap of our margin of error no greater than 50%, Cumming and Fitch say that that's probably a difference of close to 0.05. With no overlap, if we have overlap, or zero overlap between our upper limit of this and our lower bound of that, we can interpret that as a difference that's consistent with some value to be less than 0.001. This is really, really nice for secondary analysis of someone else's stuff. Let's say they didn't actually compare these, or they have a bunch of means in there that they didn't specifically test. You can go through, calculate confidence intervals and say, all right, do we see an overlap in this confidence interval that exceeds about 50%? If it's less than about 50%, you can say, well, assuming that one, you have samples of at least 10 and your margin of error across your two confidence intervals isn't greater than a factor of 2, right? So as long as you have reasonably comparable margin of error and reasonably large sample sizes, not even reasonably large, pretty small sample sizes still, you can start to infer things about, it's not an exact test, but you can make fairly reasonable predictions about whether or not you have a reliable difference across those two if you were to run a statistical test. And again, had people gone through and read the Cumming and Fitch article? Okay, go through, take a look. One thing you have to be careful of, if this is sort of my scores on day 1, my scores on day 2, then you've got a paired test, and you have to be careful with that. But for independent tests, this for me has been an incredibly useful technique to just to go through and look at people's data and say, I don't know, how comparable are that? here, if you wanna go through and do for this example, we end up with, an average margin of error across these two groups of 4.658, okay, and we have an overlap of 1.31, right? So if we take the upper bound of this and subtract it from the lower bound of that, we get about a 1.1 or 1.31 difference. If we take this and divide it by that, percent overlap, about 2.281, right? And so based on Cumming and Finch's rules, rules of looking at some of this stuff, we would say, yeah, these are reliably different. Now, here we have the mean standard deviations, all the stuff we just calculate a t-test if we wanted to, but sometimes you won't. Sometimes you just get this stuff and you can go through and kind of eyeball and say, all right, because there's this idea that, oh, if your confidence intervals overlap, then your groups aren't reliably different. That's not the case. You can have overlap in your confidence intervals as long as your overlap doesn't exceed about half of your margin of error, or your average margin error, you can infer a reliable difference between those groups. So some stuff on reporting confidence intervals. Any questions about this stuff? Okay, cool. Go through, finish up, make sure you're giving yourself some time to finish up problem set 2. What I will do by tomorrow is I'll have problem set 3 up there, kind of hit you guys sort of back to back to back, but once we get into some more involved sets that are actually using data, are going to require a little bit more of you. We're not going to be doing sort of weekly sets, but for these first couple of weeks, just to get on track, get practice up with this stuff. Tessa, I know if you have any questions or anything comes up, again, have these to us. So shoot an electronic copy to both Tess and I so that we both have it for our records before noon on Friday, and then try and have that hard copy, make sure that Tess has a hard copy in the box along with your written answers, okay? You don't have to type up all your hand calculations in a format, right? Just make sure that any hand calculations that you have are reasonable and legible and things like that, so we don't have to spend 8 days trying to figure out like what goes up with where. Awesome. All right, thanks guys. And girls. Girls.